Okay, so we're talking about optimizing a nonlinear program, and we may see that that's a minimization problem with no constraints. So our analysis will be focusing on the objective function. Okay, let's call it f of alpha beta. Then we're going to do what? Well, we want to talk about convexity. So we talk about gradient and Hessian, right? So the gradient and Hessian can be obtained in this and that way. So I don't want to do the complete derivation here because you should already be able to do it by yourself. If you differentiate your objective function by alpha, then you're going to get this one, okay? So you may put these two here and you differentiate the whole thing here and you get a negative term. So that's why you get a negative term. If you are not too familiar with this, try to do it once by yourself. Okay, for beta, that's the same thing, so I'm going to skip it. And then you do your Hessian. So for example, you take this one and then differentiate this guy with alpha again. You're going to get 2n. Why is that? Because alpha is here. This is a linear function of alpha. So alpha, after your differentiation, goes away. You have a negative number, they cancel each other, and you basically get summation of 1. That's how you get n, all right? If you do the differentiation of this with respect to beta, then pretty much it's the same. It's just that now this is not 1 anymore. Inside your summation, it is xi. Okay, so that's how you get your Hessian. Now, please try to help yourself by doing the derivations. And then we now show the objective function is convex. Why is that? So we apply the rule regarding leading principal minors. So we want this and the whole thing, the determinant of the whole thing, both to be positive or non-negative. So how that is true? So first, this is of course true, right? This is positive. And then regarding the determinant of the whole thing, pretty much we are doing this times this minus that times that. Okay, we get this one. So all the thing remaining from my point of view is high school arithmetics. But anyway, you get some hints here. So the first thing is that once you multiply the whole thing here, x1 plus x2 plus blah 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 plus xn, and multiply it by yourself, you're going to get several terms of xi squared. That's how you get here from n to n minus 1. Okay, so that's one thing. And also, you get several cross product terms. And after some careful eliminations, careful arrangements, you're going to see that all the things goes to the summation of several square terms. Okay, so that can be done. And once you do that, you immediately see, oh my God, this is non-negative. So the objective function is indeed convex. Awesome. Or alternatively, there is another way that maybe you will feel better. So let's say we define another function. So our f is the objective function, is still this one. But now for each I, we define fi. Okay, so for fi is just regarding data point xi. And then for xi, you may simply take out take the square and get these 6 terms. All right. So with this, now it may be, I hope it's very simple for everyone to do the differentiation and get the Hessian matrix. So now your differentiation is respecting alpha, alpha, beta, beta, okay? And then you're going to see that all the things goes to here, and that simply tells us that this is a convex function. Because very quickly, you don't need to do some weird derivations or calculations. This is clearly positive semi-definite, okay, according to leading principal minors. So fi is convex for all I. Now the only thing remains is to show that the summation of convex functions is also convex. So this is actually very simple, all right? So in general, this is true, and I'm going to skip the proof. If you are interested and if you don't know how to prove it, just type the sentence to whatever search engine you have. Somebody will tell you. Or if you want to do it by yourself, don't forget that we are talking about twice differentiable functions. Okay, so if you have a summation and you have several functions here, if you want to show the second order derivative of this function is some kind of positive or positive semi-definite, then you do it for everyone, and then pretty much you're done. All right, so try to help yourself to do this. Okay, so in any way, we now are able to solve the problem because we have shown that this is indeed an unconstrained convex program. Okay, that carefully designed simple linear regression model is an unconstrained convex program. So now we have two options. Either we use numerical algorithms like gradient descent, Newton's method, whatever, to try to solve for the optimal alpha and beta. That can be done. But of course, because this is unconstrained, convex, and actually if you look at it carefully, it is quadratic. Okay, all of the objective function is a second order polynomial. So if we take a look at the first order condition, which is necessary and sufficient, then immediately we get two linear equations regarding alpha and beta. Okay, that's something your optimal alpha and beta must satisfy. So this is your first order derivative with respect to alpha. This is respect to beta. They should get to 0, and that's how you get two equalities for alpha and beta. Alpha and beta. Okay, so after several arrangements, you're going to see that alpha is here, beta is here. You get the coefficient for alpha, coefficient for beta. I hope this is not too difficult for you to check by yourself. So you also have alpha here, beta here, coefficient. So basically, now you just have a linear system, which is a 2 by 2 linear system, 2 variables, 2 equalities. You know how to solve it, right? Gauss-Jordan elimination or whatever method you like. You actually can get the closed form formula or analytical solution for alpha and beta. Now you know how to do it. Then once you do it, please try to do this by yourself and compare your result with your statistics textbooks or any online resource you have. You will see that, oh, okay, so for linear regression, everybody use the formula. How to get it? At least there's one way to solve the nonlinear program we just presented to you. Okay, so maybe for many of you, you have used computer programs, statistical software to calculate alpha and beta and see your regression reports, whatever. Now you know why it can be solved so easily, because you have a closed form formula.